Hello, everyone, and welcome to Chapter 4, Alkanes and Cycloalkanes. And we are recording the lecture video for Part 2 of this chapter. Head on over to the PowerPoint slides. Okay, we're going to start by talking about section 4.4, which is the relative stability of isomeric alkanes. You can see from this graph that we're looking at stability by actually looking at heats of combustion for 3 different octane isomers. And when it says isomers, in this case, it's talking about constitutional isomers. You can see that those 3 structures all have the same molecular formula, but different atom connectivity. So those are all considered to be different octane isomers. And the reason why we can compare their stability directly through heats of combustion is because when you combust these octane isomers, because they have the same molecular formula, they're going to form the same number of moles of carbon dioxide and water. So the products are all the same energy. And then if we measure the amount of energy given off during the combustion, that will be the heat of combustion. And then we can look at relative stability based on the energy that's given off during the combustion, since that is an exothermic reaction. So what you can see here is the straight chain, what you might call the normal alkane or the normal octane, gives off the most energy. And as you increase the amount of branching in the structure, less and less energy is given off. So that should tell us that branching makes a molecule lower energy, which also means that it's more stable. So that's interesting. And if you kind of looked at this and didn't know anything about octanes, which of course are used in gasoline, you might think that the straight chain octane is the most valuable for gasolines because it gives off the most energy. But actually the opposite is true, and the branched alkanes are considered to have a higher octane rating and are therefore more valuable in gasoline. And the reason for that are the branched alkanes have a greater ability to be compressed in their gaseous form. So as you know, gasoline is a liquid, but it gets vaporized before it goes into the engine, specifically the piston cylinders. And then that gas gets compressed. And the idea is that it should be compressed, and then the spark plug will ignite it, and that energy will cause the piston to expand, and then that will be converted into work, which moves the car. So the idea is that the branched alkanes have a greater compression ability, which actually makes for greater performance of the gasoline. What happens if you overcompress a gas mixture beyond its limit? What can happen if you do that is you can have what's called spontaneous ignition, where the gasoline mixture ignites because it's been compressed, not because the spark plug has caused it to ignite. And that can cause what's called knocking, engine knocking or pinging, which damages the engine over time. So actually these branched alkanes with a higher compression limit are actually more valuable in gasoline than the straight chain ones, even though they don't give off quite as much energy. So where do we get all of these alkanes? Well, one of the ways we can attain them is through petroleum. And petroleum literally means rock oil. Basically, it is oil that, as you know, we can drill out of the earth. And there's a limited supply of that, which is why there's all sorts of interest in renewable energy. But you can still drill petroleum, right? And from that, you can get different sized alkanes, and they can be separated by distillation. And distillation basically takes a liquid and heats it up, and the things that are the most volatile with the lowest boiling point will sort of rise as a gas, right, up the column, and then eventually be condensed as it's cooled down later back into a liquid. So the things that have the lowest boiling point are the smallest alkanes. So for example, fractions that contain alkanes with only 1 to 4 carbons would come off before fractions that contain alkanes with a higher number of carbons. And you can see the relative boiling point goes up as the molecules get larger due to increased London dispersion forces. So that these smallest alkanes are actually used as natural gas, for example, methane, and also petrochemicals, and can be used as building blocks for making plastics. The next size would be solvents. Maybe you've heard of pentane or hexane, that sort of thing. So those can be used as organic solvents. And then the C5 to C12 can be used in gasoline. And again, octane would be C8, but there's a range that can be used. And then as you get higher, we're looking at kerosene, diesel, oil and grease, and then wax and asphalt and tar. So if we focus in on the gasoline component, right, that actually only makes up about 19% of crude oil, which is not enough to meet demand. So there's various processes that have been developed in order to get more gasoline-sized molecules out of crude oil. And one such thing that you can do is a process called cracking. Cracking takes larger alkanes and breaks it down into smaller ones through a reaction that utilizes hydrogen gas at high temperature and pressure. And also, remember we talked about how branched alkanes are more valuable than straight chain alkanes. So we can actually convert straight chain alkanes into branched alkanes and aromatic compounds through a process called reforming, which again helps to create what's called a higher octane movie. Okay, and then after these processes, the yield of gasoline from crude oil goes up from 19 to 47%. All right, moving on to section 4.6, we're going to be talking about drawing what are called Newman projections at this time. And Newman projections are a way of drawing molecules that help us analyze different bond rotations because single bonds can freely rotate in a molecule. And so we want to see as they rotate, what are the different energies that the molecule goes through? What's a higher energy conformation versus a lower energy conformation for the molecule, right? So what we have, right, are different ways of representing molecules. So starting from something you might be a little bit familiar with, which is the wedge dash notation. Remember that straight lines mean that that's a bond in the plane. And then a wedge means that the atom is coming out of the plane at you. And a dash means that the atom is going back into the plane. So that's one way of looking at it. But if we actually rotate this molecule, right, we can look at it in what's called a seahorse conformation. And this actually helps us sort of look down a carbon-carbon bond where it's at a slight angle. And then you can see sort of straight on where the hydrogens are. And then a full-on eclipsed conformation is the Newman projection. Why I call it an eclipsed conformation is basically what you're doing is placing your eye over here and placing the back carbon right directly behind the front carbon such that the entire thing is eclipsed by the front carbon, right? So you actually, if you were looking down this carbon-carbon bond, you wouldn't even see the back carbon because it's directly behind the front carbon. So then the Newman projection looks like this. And this dot here in the center is the front carbon. And then because we can't see the back carbon, we create it as a big circle. And then we have the different atoms attached to the front and the back carbon sort of protruding out of either the center point or the back carbon, which is the circle. You can see that the red hydrogens are up and sort of down and to the left and down and to the right. You still see that here with it going up, down and to the left and down and to the right. And then the back carbon has the hydrogen pointing straight down and then up and to the left and up and to the right, just like you would see on this back carbon. Right? So these Newman projections are really ideal for comparing the relative stability of possible conformations resulting from single bond rotation. Specifically, we would be rotating the carbon-carbon bond here, as we'll look at eventually. Okay, so what we're doing, right, is we're placing our eye, and it, you don't obviously have to do that, but you want to imagine yourself looking down the carbon-carbon bond here, right? And so what we'll do is, remember that dot is going to be the front carbon and the circle will be the back carbon. And then we'll see where the hydrogens are, right? And then place them on the carbon. So ask yourself, what is the bond angle, right? The true bond angle between this hydrogen, carbon, hydrogen. So you might think, well, okay, this carbon is tetrahedral. So the bond angle is 109.5 degrees, and you would be right. It is 109.5 degrees. But the Newman projection kind of flattens out the molecule. So it takes what is a 3D structure and flattens it out. So on 2D paper, the bond angle would be 120 degrees. So it looks like 120 degrees, because of course we know a circle is 360 degrees. And if there's 3 atoms, right, then the farthest away they can get is 120 degrees. So when it's flattened out, it looks like 120 degrees. But of course, it's truly not flat, right, in 3D, and so it's really 109.5. Okay, so what we'll see is that one of the hydrogens will be pointed straight up, right, from this person's perspective. The other one will sort of be on a wedge coming out of the plane of the screen. And then the other one is on a dash, sort of pointed into the other side of the screen. You see that the one pointed straight up, and then the one that's down and to the left, down and to the right. And then on the back carbon, and it's not drawn very well here because there aren't any dashes and wedges, unfortunately, in this picture from the book. What it's trying to show you is that there's one hydrogen pointed straight down, and that would be this one on the back carbon. And then there's a hydrogen that's on a wedge coming out to the left, and the other one is sort of on a dash going back and to the left, and then the other one was to the right. Right? So sort of back and to the left and up and to the right, right? And that would be those two here. We're really sort of looking at this from a certain way and sort of flattening it out in 2D. So look at another example here, and this one doesn't have all the atoms drawn in, right? So this one is drawn in line structure. So what you want to do is imagine, right, all of the atoms, including the ones that are not shown. So for example, what this person is doing is looking down this carbon-carbon bond. So we say this is the front carbon, and it's represented by this dot here. The back carbon is represented by the circle behind it. There's a methyl group, which is this CH3 group, right, pointed straight down, which is why you see the CH3 pointed straight down on this front carbon. And then there are 2 hydrogens as well, not drawn in, since it's a line structure. And those are on a wedge and a dash, right? And this would be the one on a wedge. This is the one on the dash from the person's perspective. And then as we go to the back carbon, what we see is directly up is the chlorine, which is why you see this chlorine directly up. And then down and to the left is the methyl. And of course, because carbon makes 4 bonds, there's also a hydrogen on a wedge coming out of the plane of the paper, and that would be this hydrogen here. So this is a skill you want to be able to develop to go from a line structure and to be able to draw a Newman projection of that structure. If you're having trouble seeing this from 2D to the Newman projection, I really recommend you get out your model kit, which hopefully you purchased. And if you didn't, you can get an organic chemistry Molly-Mod kit, like from Amazon or some other website online. I think you can also purchase them at the bookstore. And you can build, right, a molecule like this and play around with perspectives, being able to sort of visualize or look down a carbon-carbon bond to be able to see what that would actually look like. Okay, let's do a few more definitions, right? So remember I talked about the fact that both carbons were tetrahedrons. So all the bond angles are 109.5. But as it's drawn flat on 2D paper, we're going to say that this is 120 degrees. So if this is 120 degrees, then the angle between the hydrogen on the front carbon and this other hydrogen in red on the back carbon is 60 degrees. And so that 60-degree angle on adjacent carbons is called the dihedral angle, also known as a torsional angle, right? And this is the maximum distance atoms can get away from each other, right, in a Newman projection. So there's different conformations that we're going to be looking at when we start rotating the carbon-carbon bond in a compound that's drawn as a Newman projection. We're going to encounter conformations that look like this, where the dihedral angle is 60 degrees. And we're going to call that a staggered conformation. And because the atoms are the farthest apart they possibly can be, this conformation is the lowest in energy. If you rotate, for example, the front carbon, so imagine rotating this carbon sort of in a clockwise direction, this hydrogen will move over here, right? This one would move over here, and this front one would move up there. So eventually, as soon as this hydrogen gets directly in front of the hydrogen on the adjacent back carbon, then we have what we call an eclipsed conformation. Now this doesn't look completely eclipsed, and that's because we can't draw a hydrogen atom directly over another hydrogen atom and know that there's two hydrogen atoms there. So it's really drawn like slightly askew of complete eclipsed. But what it's meaning to show you is that the back hydrogen is entirely eclipsed by the front hydrogen. Like you can't even see it if you were looking down the carbon-carbon bond. Those hydrogen atoms are much closer together than in a staggered conformation. If you don't believe me, make a model, right, of ethane. So make ethane and then go between the staggered and eclipsed conformations and then visualize how far apart the hydrogens are in those different conformations. Entirely eclipsed, which would be a 0-degree dihedral or torsional angle, is the highest energy conformation. And then the difference in energy between these two conformations is due to what we call torsional strain. And the difference is 12 kilojoules per mole, right? So an eclipsed conformation has maximal torsional strain because of the 3 eclipsing interactions. And again, that's just the difference in energy between an eclipsed and a staggered conformation. So let's look at ethane as you visualize it in a Newman projection, starting from a staggered conformation. Remember, we're looking down the carbon-carbon bond. In ethane, there's 2 carbons, right? So you're looking down the carbon-carbon bond. And you start off with all the hydrogens entirely staggered. And then just to visualize the rotation, because they're all hydrogens, we're going to make 2 hydrogens red. And if you were doing this with a model, you could, for example, use a different colored ball instead of the white colored balls for hydrogen. Let's say you use a red ball or something like that to help you keep track of certain hydrogen atoms during this rotation. So we're starting off with the 2 red hydrogens opposite each other. And then we're going to be doing 60 degrees at a time rotations of the front carbon. And so you can see the back carbon is basically just going to stay exactly where it is. And we're just going to rotate the front carbon 60 degrees clockwise. And so as we rotate the front carbon 60 degrees clockwise, this red hydrogen moves 60 degrees to the right, and you can see it moved up here. Right, so now we reach our first eclipsed conformation, which of course is 12 kilojoules per mole higher in energy than the staggered conformation. If we do another 60-degree rotation clockwise of the front carbon, we reach this staggered conformation, right? Keep going and we reach our second eclipsed conformation. We go 60 degrees more and we're at another staggered conformation, right? Followed by an eclipsed conformation and then back to the original conformation after a total of 180 degree rotation, 60 degrees at a time. So you can see we go from the lowest energy possible conformation, and every time you reach a eclipsed conformation, it's 12 kilojoules per mole higher. So if it's 12 kilojoules per mole higher in energy than the staggered conformation, that would mean that each of these hydrogen eclipsing interactions would be 4 kilojoules, or you can think of it as it costs 4 kilojoules to eclipse 2 hydrogen atoms compared to having them in a staggered conformation, right? So with a 12 kilojoules per mole difference in stability, 99% of the molecules will actually exist in a staggered conformation at room temperature, as opposed to an eclipsed conformation. The difference in energy between an eclipsed conformation and a staggered conformation can also be rationalized by the presence of stabilizing interactions in the staggered conformation. So these stabilizing interactions are not going to exist in the eclipsed conformation. Specifically, when all of the hydrogen atoms are staggered, we can look at sigma bonding molecular orbital interactions with an anti-bonding sigma star molecular orbital for a different carbon hydrogen bond. So this is a carbon here at this juncture, right? And it's bonded to a hydrogen. And anytime you have a bond, right, it's going to be using an orbital to do that. And so this is showing the sp3 hybridized orbital that it's using to make this carbon hydrogen bond. And of course, it should be overlapping with the hydrogen's 1s orbital, but they've left that out for simplicity. And so what you can see here is that there's side-to-side overlap with the anti-bonding molecular orbital for the carbon hydrogen bond that's directly opposite the first carbon hydrogen bond. So this carbon hydrogen bond would also have a bonding molecular orbital, but the red lobe would be pointed in the opposite direction, and the blue lobe would be pointed this way just because of the direction of the bond. And that would be filled. So we would not want to have a filled-filled interaction here. So what we're looking at is actually the anti-bonding sigma molecular orbital, which is empty. And if it's empty, right, and it's right next to a filled orbital, and they're close enough together, there can be this side-to-side overlap. And the electrons in the bond can actually delocalize into this other space and help. And of course, anytime you have electron delocalization, it stabilizes the electrons. And there would be 3 sets of this interaction going on for each of these hydrogens, right, with the opposite hydrogen on the other carbon. So this is one molecular orbital perspective way of explaining why the staggered conformation is more stable than the eclipsed conformation. Okay, let's continue on by looking at that same sort of energy diagram for the conformational analysis of propane. So with propane, you need to, if you're making a model, you want to attach 3 carbons in a row, right? And have all the hydrogens attached to those 3 carbons. But in a Newman projection, we're still only looking down one single carbon-carbon bond. So what you'll see is that one of the substituents on the carbon, in this case, the front carbon, is going to be a methyl group. in propane. So we're looking down one of the carbon-carbon bonds where there's a methyl group on the front carbon. We've sort of highlighted this in red. What you can see as you do these 60-degree clockwise rotations of the front carbon is, again, we're going from staggered to eclipsed conformations, and those are alternating. But if you look at the energy difference, now we're at 14 kilojoules per mole. And that can be attributed to the fact that this methyl group is a bulkier group than a hydrogen. So while we still have two sets of hydrogen on hydrogen eclipsing interactions, now we have a methyl on hydrogen eclipsing interaction, which is even higher in energy because the methyl group is larger and it's going to sterically crowd the other hydrogen even more effectively. So if the barrier for rotation, again, from staggered to eclipsed is 14 kilojoules per mole, that's 2 kilojoules per mole more than for ethane, what we can do is a similar sort of calculation than we did for ethane. Knowing that the hydrogen on hydrogen eclipsing interactions costs 4 kilojoules per mole, and we subtract that each of these, which would be a total of 8 from 14, we end up with 6 kilojoules per mole left over, which must be the cost for eclipsing a methyl and a hydrogen atom. Okay, going on from propane, let's look at butane. And again, I encourage you when you're thinking about this to make a model and visualize yourself looking down the carbon-carbon bond, rotate that front carbon 60 degrees at a time so that you can see what it would look like to go through a 180-degree bond rotation of butane in a Newman projection. So what we're going to see here is that as we go through this rotation of that central carbon bond, there's going to be some differences in energy. And that's because the eclipsed conformations are not all equally stable or unstable in this case. So there's one that's particularly unstable compared to the others. And then also, interestingly, the staggered conformations are not all equal. Having the two methyls opposite each other is not as sterically crowded as having the two methyls adjacent to each other, even though these are all staggered conformations. So you can note that there's multiple energy levels for both the eclipsed and the staggered conformations for butane. Again, we are looking down the central carbon-carbon bond of butane. So now that there was two methyl groups attached to those, the front and back carbon, respectively. And we're going to start with those methyl groups opposite one another. And then again, we're just going to do the same analysis where we're rotating the front carbon 60 degrees so that it goes in between staggered and eclipsed conformations. So what we see is as we rotate the front carbon 60 degrees, we end up with two methyl hydrogen eclipsing interactions and one hydrogen on hydrogen eclipsing interaction. We probably could have predicted this energy difference because we know how much energy it costs to eclipse two hydrogens versus a carbon on a hydrogen. Right? The hydrogen on hydrogen was 4 and the methyl on hydrogen was 6. Right? So 4 plus 6 plus 6 is 16. Continuing our 60-degree rotation, we go back to another staggered conformation. However, interestingly, this is not the same energy as the first staggered conformation. Specifically, this second staggered conformation is 3.8 kilojoules per mole higher in energy than the first staggered conformation. Notice that it's still much more stable than any eclipsed conformation, but not as stable as the first staggered conformation. And think about these two bulky methyl groups, right? They're much farther apart when they're opposite each other than when they're 60 degrees apart. As we rotate another 60 degrees, we end up with both methyls eclipsing each other. That's going to have the greatest strain of all, because again, now we have two bulky groups directly as close to each other as possible as they can get. So if we think about how much does it cost for two methyls to eclipse one another, well, we just have to subtract how much does it cost for the hydrogen eclipsing interactions. We know each one is 4, right? So 19 minus 8 leaves 11. So it actually costs 11 kilojoules to eclipse two methyls, right? Which is a lot more than the other eclipsing interactions we've seen so far, which are 4 and 6. And then as we continue, we get the other conformation where these two methyls are next to each other, but still staggered, right? Continuing on to sort of the mirror image of this eclipsing interaction, same energy because we have the same types of eclipsing interactions, right? And then back to having the two bulkiest groups opposite one another. We actually have some names or some terminology for these that you'll want to know. When the two bulkiest groups are opposite one another, we call this an anti-relationship. When they are still in a staggered conformation, but right next to one another, we call this a gauche conformation. So again, the gauche conformation is 3.8 kilojoules per mole higher in energy than the anti-conformation. That's because these bulky groups get a little closer together in that gauche conformation. But of course, a gauche conformation is still a staggered conformation. So relatively speaking, it's still much more stable than an eclipsed conformation. Right, and then this is that energy calculation showing us that we can actually figure out the cost of eclipsing two methyls, and it's quite high, 11 kilojoules per mole. And it has to do with what's called a torsional strain and a steric strain, right? The torsional strain has to do with the angle because it's a 0 degree angle, torsional angle, that gives it torsional strain, and a steric strain because it's a bulky group. So this is the energy cost of eclipsing certain groups. And we've seen all of this in our analysis of the different Newman projections we've looked at so far, right? And then the type of strain, right? The torsional strain refers to the angle strain. And then the steric interaction is when you have two particularly bulky groups. There's also a interaction of trying to get those two close together. And then notice that the gauche conformation, the strain is only due to a steric strain because the two groups are bulky. There's no torsional strain because it's at a 60 degree angle, torsional angle, and that's considered to have no torsional strain if you're in a staggered conformation with a 60 degree torsional angle. Again, as you go from 60 all the way to the extreme of 0, you're increasing the amount of torsional strain. Okay, that is it for the lecture. I tried to make that pretty quick so that you guys could spend more time analyzing your models, which is going to be really helpful to get you to visualize all these different conformations due to bond rotations and to work on the activity.